All right, here goes part 3, our final part talking about linear relationships. Part 1, we talked about how we could represent linear relationships in tables. Part 2, we showed how we could then represent that information in linear equations. And now our third and final part, we are going to show linear relationships on a graph. Remember, the context that we're talking about this problem is in terms of masks that hospitals are using for the COVID-19 pandemic, making sure that hospitals have enough masks to keep their workers safe. Something that hospitals likely had to do when they're trying to plan out how long their stockpile of masks will last is put it into a table equation and of course a graph to visually represent how many masks they are using each day. All right, let's take a look at how we can show this on a graph. Here's my graph that I prepared. It shows the two variables that we are writing relationships representing between. Remember, those two relationships are days versus the number of masks that each hospital uses. All right, remember I talked about independent versus dependent relationships and variables in the last video. Whatever is the independent variable goes on our x-axis down here. And whatever our dependent variable is goes on our y-axis up here. The number of masks depends on the number of days that go by. Let's go ahead and put the information for our 3 hospitals onto the single coordinate plane. And we are going to look at how the lines, the graphs that we make for each hospital compare to each other in a linear relationship. All right, so remember hospital number 1, we showed that they used 150 masks per day. So of course, at day 0, they had used 0 masks. So I'll put a dot at 0, 0, which we call the origin of the graph. After 1 day, they used a total of 150 masks. I didn't clarify this, but take a look at my scale. Over here, each of my grid lines is worth 50 masks. I labeled 100, 200 masks, 300 masks, 400 masks, and the lines in between then are 50 masks. So 50, 100, 150. Day 1 is 150 masks. Day 2, they use 150 more. That's a total of 300. Day 3 is a total of 450 masks. Day 4, they used a total of 600 masks. And after 5 days then, they used a total of 700. I'm about to connect all of these dots to show the constant change of number of masks over time. Before I do so, what do you notice about the shape that those dots are making? How are they lining up? Are they in a straight line? Are they not in a straight line? What do you notice? There's a line that I drew through all those dots that we just plotted, all those coordinate points, and what do you notice? It did make a straight line. That's going to be important. Let's notice if that's going to be the same for the other 2 hospitals as well. Remember, this blue line is hospital number 1. Hospital number 2, next up, remember they used more masks. They used a total of 200 masks per day. Just like hospital number 1, after 0 days, they had used 0 masks. So our first coordinate point is right there again at the origin. However, after day 1, they used a total of 200 masks. So I go over to day 1 up to 200 and I plot that point. Another day goes by and they use 200 more masks. So now they're at 400 total masks. Day 3, they used a total of 600 masks. Day 4, they used a total of 800. And I connected all 3 of those. And I connected each of those red dots with my red line to represent the change over time for hospital 2, how many masks they were using. Again, same question, what do you notice? What kind of line did this graph make? Just like hospital number 1, this line for hospital number 2 is also straight. Right now, I'm going to let you know that when we talk about linear relationships and linear graphs, that means that it's always going to make a straight line because it means that it is constantly changing by the same amount. Just like we saw in the tables, the numbers were going up by the same amount each time. In the equation, we were multiplying by the same number each time. Now, in a graph, the dots are going up by the same amount each time, making a straight line. Now, are these the same line though? Is one more steep than the other? Let's take a look. What about hospital number 3? Do you have any expectations or guesses as to what the line for hospital number 3 will look like? Remember, as a final reminder, hospital number 3 is also using 200 masks per day, but they also started, that starting point we talked about was 50 masks when they donated 50 masks to that grocery store. So at day 0, unlike hospital number 1 and hospital number 2, at day 0, they didn't start with 0 masks. They started with a total of 50 masks. So our starting point is at day 0, they already used 50 masks. Then they used 200 masks per day. So day 1, they used 200 more, which means they used a total of 250. Day 2, they used 450, like we already talked about. 650 on day 3. Day 4 was a total of 850. And day 5 was a total of 1,050. Funny how those dots look like they are very, very close to hospital number 2. Let's see what that line looks like though. Taking a look at the green line that I just drew, it also looks like it's a straight line. Remember, that's hospital number 3. It's also a straight line going up by the same amount each time, which means, yes, that is a linear relationship. Now, does it look like it's the same as the red line? Does it look like it's the same as the blue line? What do we think? Well, if we compare just the red and the green line, we have a word for those kinds of lines. Lines that never cross, like think about railroad tracks. They are called parallel. So those are never going to cross because those lines are going up by the same amount each time. Whereas the blue line isn't quite as steep. It's not going up as much each time. Still linear, just not as steep. We have a special word for that relationship. How steep a line is, how quickly it's going up a graph, is called the slope. Slope, that's what it looks like, S-L-O-P-E. Slope is how steep the line is, how quickly it's going up. In the last video, we looked at our linear equations, y equals mx plus b, and I said we would have some more information about what these letters mean. Which of these letters stands for the slope, do you think? In an equation, which of these parts of the equation will tell us how steep the line will be or how much it's constantly going up by? If you said m, the constant multiplier, then you're right. That m, the constant multiplier, is also telling us what the slope will be, all right? Now, we also notice something else that's important about the green line. Does the green line go through the origin, 0.00 of the graph? No. It crosses one of the axes at a different place. Does it cross the x-axis or the y-axis on this graph? It crosses our y-axis right here at 0.050, all right? We talked about how that's because they had a starting point of 50. They started by using 50 masks. On the graph, we can see that that starting point tells us exactly where the green line is going to cross or intersect the y-axis. So in an equation, yes, b tells us the starting point. It also is called the y-intercept. So, yes, we know how to identify those things in an equation. We know that the slope is what we're multiplying by, and the starting point, which we also call the y-intercept, is what we are adding. All right, that's a lot of information about linear relationships. My hope is that it is making sense as we're talking about linear relationships in terms of tables, equations, and graph in the context of using masks at a hospital. I'm going to post a couple questions for you to figure out what do you understand, what don't you understand. My hope is that you can use these videos next year in 8th grade. In 8th grade, you're going to talk about different types of relationships, exponential relationships, but you're going to need to understand some of these things about linear equations, tables, and graphs. So my hope is that you could always revisit these videos to remind yourself of what you already know, all right? Hope that you're staying safe, hope that you're staying healthy, and I hope to see and hear from you all very soon.